and now the angle slowly goes down, and we never really have this resonant property. So that's if you look at the continuous domain and you see these poles, just that you know what they really mean. If they're really steep from the origin or close to the imaginary axis, the angle, right, then you know you don't have a well-damped system.
Okay, so the real part more greater to, like if the real part is larger than imaginary, then it's more damped system, right?
If what?
The real and imaginary part in conjugate poles.
Yeah.
Let's say real part is more than the imaginary part, then
Yeah.
it's like more damped system.
I mean, the relationship between them tells you how well the system is. That's correct, yeah. So if you get a bigger real portion, you always dampen the system more. But it's really about the angle. Right? It's really the angle that tells you how well it's damped. Okay.
I've seen an equation which says that for cos theta less than 0.727, that's 1 over square root of 2,
Yeah.
there will be a resonant peak, and if it's more than that towards 1, there will not be.
Yeah.
It's like a standard equation in control.
Yeah.
But
And
there's
this is all true, and you can all use this, but again, if you just use this and place the poles, you wouldn't have come up with our solutions, right? And you can try these, and you will see that you never place two eigenvalues in a proper fashion, and you will not get the same dynamic stiffness, and you will not get the same dynamic results. But yes, all of these things are absolutely true, and it's good to evaluate the system if you just look at the poles, that you have an idea what's going on. But to really see all the other things inside, right, you cannot see in the poles and the whole transfer function. It's hard. Maybe someone can, I can't. Right? Like the concepts I taught you is really in the physics-based block diagram. There you really see what's going on and what can be an issue and what not. Right? If you decouple R, what would this do to our poles? And you can play around with it, sure, but it's way hard to be really creative with this, I think. Anyway, so that's that was now for the continuous time. In discrete, this looks a little bit different. And what do we use in discrete domain to describe our system? What domain do we use? Does anyone know?
The Z domain.
The Z domain, exactly. What does the Z domain do? What is it? What does the Z stand for?
The Z transformation. The Z transformation.
sampling.
It's sampling. It really comes from sampling, and that's right. And if we want to maybe describe what the Z itself means in respect to the continuous domain.
The delay operation.
It's a delay, absolutely. And how do you describe a delay in continuous domain?
E over T
Basically,
J S T.
E over ST, that's correct. So, and if you look at any Laplacian sheets or so, oh yeah, thank you. You will see that if you have a delayed function, since you have f of t minus t, this will be
F of
f of s
multiplied by E over ST.
Is it st?
or S minus Z, I forgot.
I'm not sure.
Yeah,
I'm not
minus
sure
Z
either
or
which
S.
one is which direction is the entire domain. I mess this up all the time, so don't hold me to it. It might be this or it might be the other way around. But what I know is that if it's delayed, so the minus just, I don't know if this is in the future or not, if you put minus t or plus t. So, but if it's delayed really, like one time back, you put a 1 in and it takes one time longer, that is e to the minus st. Right? So, for instance, at time 0, you put a 1 in, then after e to the minus st, you get this at time t.
Yeah.
Okay? So that is e to the minus st. And a short form to write this is z to the minus 1. That is all it is. It really is just using this information of delays, and it's only for exactly t. So that's our sampling time. If we have a sampling time, then this is the case. It's just not true for all the t's. It's true for exactly our sampling time. And that means once we're in Z domain, we only work in samples, and it's only in t iteratives, right? We go from t to t.
This is minus ST.
Yes.
Can you tell what that is about again? Those two. What happened after t?
This here?
Yes.
So let's say, no, I'm saying like this is my input,
Yeah.
and I put it into a z to the minus 1, or an e to the minus st, this would be your output. It just delays it by 1 t.
Okay.
That's what z to the minus 1 means, or e to the minus st. And so this also means that when you look at poles, right? So in Z domain, for instance, you have a transfer function that looks like 1 plus Z, for instance, or Z. That also means that my pole now is at minus 1, right? And this pole basically means that Z, the pole, is the same as e to the theta t. So that's the pole that I would have seen in the continuous domain. This pole of minus 1 would be e to the minus 1t. Right? So, and that's how we basically can describe where our pole is. And if our pole, for instance, has an imaginary portion, right? J imaginary, and the real portion, you will see that this turns out to be e to the j imaginary portion times t times e to the real portion times t. And what are these two now? This, and what is this? What is e to the j something?
It's a complex.
X.
But it really is an angle, if you think about it. It's a length of exactly 1, and I can place it just on the circle somewhere. And this is no angle information, right? So if I multiply this times an angle, it's just a magnitude, right? So this is an angle, and this is a magnitude. So what does it look like to you? It looks like polar coordinates, right? So what did we say about the real portion, or actually we haven't talked about it, but I'm sure you know this, but we should have said this at some point anyways. Where do we want our poles to be? So we said that they should be within a certain angle, right?
Yeah.
That's where we want it. But do we want them up here as well, also the same angle? No? What happens back here?
System becomes unstable.
This is unstable, right? You learned to control in your control class already. This is a no-go. This is not stable. So, if the real portion can be bigger than or it has to be lower than 0, right? If the real portion has to be lower than 0, then also e to the r, the real portion of e times t will be smaller than 1. Okay? So that means in the z-domain, and you will see the z-domain actually, we plot this like polar coordinates because that's what we do. We do an angle and a magnitude. We will see that the z-domain, we usually print this circle of a length of 1, and then we plot them inside of here because all of this room here is basically warped and is everything outside here. Okay? So everything outside of this unity circle is unstable. So we want to be really inside of this circle with the length of 1. Okay. I want to have a look at this if that's really true. So let's do some z-pole plots here. So I don't know if you can see this quite clear, but I just plotted the 2 poles we had before, up there and here, and the z-domain they're now here and here, and within the unity circle. Okay. So if I now increase the imaginary portion, what should happen? What will happen with the 2 eigenvalues in the z-domain?
They move towards 90 degrees.
I just increased imaginary a little bit. What will happen?
Angle change.
The magnitude will be same, but the angle will go closer to plus 90 and minus 90.
Exactly. So it's hard to see here because exactly on the 0.8, but as you can see, the magnitude really didn't change. This one is here, the other one is here. It was just the angle, right? So if I increase the imaginary portion in the continuous domain, we see how it moves up, but here it really moves in circles. So now I moved actually this one quite a bit up to here, and this one from 0.8 down here. And these lines here that we see, they tell you how fast the eigenvalue is. Right? Here's always like this value. You see this? These here tell you how fast it is. And these tell you how well damped it is. These are your damping coefficients. So if I increase now R, let's say, go down here. Let's get rid of this and this. Let's start with this now. Now they're here, up here and down here. And if I increase R, what will happen? The magnitude should change, right?
The angle should also change.
So the angle didn't change, right? If you think about the straight line,
Yeah, that's depending on the mass. Yeah, angle should
the angle should not change, but the magnitude changed. And if you can see, the closer you get down here, the higher the damping is. So really what happened is, we went on this straight line down here, we went here, and if you look at this, it actually got a little bit faster, right? Here's 0.3, here's 0.4, it got a little bit faster, but also way more damped.
And the other line is the natural frequency or what?
And if we look at this plot, we moved from here to here, right? So we already can see the angle got smaller, right? So better damping, and the magnitude is a little bit longer, so faster. Right? And you can see this here with these lines. That's what these grids tell you. They basically tell you what the speed and what's damping. So here we said we want this, right? So what do we learn from this? We basically learn In continuous domain, you want it between a certain angle, this is what we want. Whereas in discrete domain, we really want to be here, right? Actually, it's too far. We want to be within a certain damping, but we can't choose our speed. Right? We can be, so the closer we get to the origin, the faster our eigenvalue is. Like on the x-axis, the more we go to the left or closer to the origin, the faster the eigenvalue becomes. And the further we get back, the worse the damping. So we want to be close to this axis, and on the left, we want to be fast and damped. Okay, so this is basically the information that we get. Okay, so on time, we have work.
Can I explain once? Those two blocks.
Which one?
Like the damping and faster, that's getting confused.
So in the continuous domain, you understood it, right? So this is basically just if you were to plot y with the same angle, poles, with the same damping, you would wind up with eigenvalues on this line. Okay? That's what they plotted here for us already. They basically give us the information, what is the same angle, and the closer I get to the left, the faster I get. These are this lines. These are basically equidistant eigenvalues with the same magnitude. So everything on this circle. So they basically drew a circle, and the circle became this line, and everything on the straight line has the same damping, and they look in the z-domain like this. This is already plotted for you so that you can read these. Okay? This is your damping coefficients, and these lines here are the speed of your of the eigenvalue, or natural frequency, and the damping. Okay? We'll also have another video so you can have a look at it back again. Hopefully I captured it correctly, because flipping back and forth, the chances there that I missed something. Okay. So this was basically just to have a look back at what do these poles actually mean. Okay? This was just because in discrete domain, it will be tough to get around zero pole placement. There's sometimes you can, but sometimes you just have to use these concepts. So I want you to be to know what you're doing, basically. Okay? Feel comfortable with it, because the concept is not really all that hard, but it's not as intuitive as playing around with differential equations and decoupling and stuff. But I wanted you to have a look at it and understand what's going on. Okay. So now that we talked about all of that, we want to get into actually discrete modeling. And there's different words for this. I very frequently use the word direct discrete modeling. Some people call it correct discrete modeling, I don't know. What it is really it solves the differential equation for discrete time. And this way it is an actual real solution, because you solve the equation. Okay, and this works in discrete time very well. And there's two really nice ways to get there. One is a little more tedious than the other, but I will teach you the tedious one first, because it has actually more degrees of freedom, or it's easier to use degrees of freedom. But first of all, let's see what the discrete modeling really is about. And we start with, again, with example 2. And it's also really nice for you that we always keep using this because it's actually from differential equations very close to the current control. It's the, again, the force to the mass, right? And with friction coefficient, and this would be our disturbance. And with friction, I don't know what, usually very often we use C for friction. What do we use there? B? Yeah, I think B is more rotational, but it doesn't matter. We just have to talk the same language. So, before we now use the differential equation and so on, right? But now I want to talk about how does it look in real life. So in real life, now you would have like a force reference, right? But it would be in the z-domain, or at least in discrete time. You could also use of k, but if you're in discrete time, this would be in the z-domain. And then we have our analog to digital device, right? It could be our converter or inverter, whatever we have here. But what it really is a latch. I don't know if you know what the word latch means. It basically means that you hold something. Mathematicians call this a zero-order hold. If you want to do it in MATLAB, you also have to use a zero-order hold, Z-O-H. And what it does is, you basically, whatever you put in there, it puts it out and holds it for one period. Right? Whatever your FA is, even if you put something continuous into this, it will hold the value exact at the sampling point and hold it for one period. Okay? And this is what your analog to digital conversion does. You give it a 5, and what it does is, whatever it was before, it steps to the 5 and holds it between the time and then whatever the new value is, it will hold that, right? So that's what the latch does. So we have that in our system no matter what. And after that, we have a function time, but it is really constant during 0 to t, right? And then we have our differential equations now, because this is the actual system. It is both happening. And this should have been an integration. This integration because everything is in t. And this would be our, oh, we use B, right? Sorry. This is the friction, right? And here we have our disturbance. This is clear, right? So up until here, this was the exact same differential equation that we had before. And now we measure this, but we do sample still. At our sampling time Ts, we get now a V of Z or V of K, whatever you want. And this is our interface to the world. This is the digital latch. In MATLAB, you also have to use a zero-order hold here. So MATLAB, you build a block zero-order hold with the sampling time Ts. And that's how you build it in MATLAB. Your input, zero-order hold, then the actual continuous system, bring it back, zero-order hold, and now you can build everything in the discrete domain back here. Okay?
But isn't it matter is already working in this domain?
It is sort of. You're absolutely right. Like what they do is actually they use forward Euler, backward Euler, or Tustin, but very, very high sampling frequency. So for your case, you're absolutely right. What MATLAB does at this point, it's numerical, it's not analytical. It will actually do a Tustin or Euler or whatever, but so much faster than what you're looking at, really, that it isn't like integration.
We can make it slow.
You can make it slow and then everything will work. You're absolutely right. But we want to have a look at this, at least in our homework. We want to look at how we want this to be quasi-continuous and see how well does our approximation of this work. Okay? So if you model the correct system, please do it like this. And then you do your approximations, or the correct discrete model, and then do approximation and see how do they compare to this. Okay? So, because what we actually want is, like, how do we design this control model? This in Z-domain is continuous. You can't design poles and zeros anymore, right? So what we really want is, we want to know what is this transfer function? What is between Vf of z and V of z? And we call this the new system dynamics. What is this in Z-domain now? This is our goal for today, to know how do we model this. And again, what approximation models would do, they would say this is a 1 over s, and they would approximate it with a something, right, with tangent or whatever. And then this is already a Z-domain transfer function, and they just keep it like this. Okay? We want to see, like, what do we think it actually is if we do correct discrete model. And there's really two ways to get there, and I'll start again with the more tedious one, and we call it the 10 steps. It's actually more than 10 steps. But for the first order system, it's really 10 steps, so that's why we call it 10 steps. It's also in the homework. And the first step we already did. It's developing the differential equation in the continuous domain. This was what we did here. Alright, first actually develop the physical system. Develop the physical system, which is this, right? And then the second would be prepare the differential equation description. The second is to get an ordinary differential equation, or a set of ordinary differential equations, which is here m dv dt equals fa of t minus f d of t. Right? We did this before, so that's step number 2.
What about the friction?
Sorry?
What about the friction in that?
Oh, yeah, where's the friction? Sorry. Also minus v times v of t. Good catch. The friction is missing. Yes. Right? The third step is to do the Laplace transform. And again, we're trying to solve the differential equation right now. So something we really have to make sure when we try to solve it is that we take care of the initial conditions.
For doing Laplace transform, we always make sure the initial conditions are 0.
Sorry?
For Laplace transform, we always assume the initial conditions are 0.
Exactly. And we cannot do this here. But in Laplace, it's very easy to implement it. We just usually leave it out. But right now, it's really important that we have it in there. We try to solve it. And so the third step is to get the Laplace transform. It's the Laplace transform. And also make sure that we include the initial conditions, which means the Laplace transform of dx of t equals x times s
Minus x of 0.
x times 1, 0. Absolutely right. Which means our differential equation becomes now m times v of s times s minus v at time 0, right? That's the first portion. And again, it's f a of v, oh, I'm sorry, it's s. Minus f t of s. And actually, for the time being, I don't want to talk about disturbances just yet. Excuse me, I'll keep this out, that will be for next lesson. We'll keep this out. Times v of s. Okay? So the fourth step would be to cross-solve for each state as needed. Cross-solve for this state, for the states as needed. In this case, it's a first-order system. We really only have one state. If we have a cross-coupled state, multiple inputs, we would at this point try to solve for one state. So we already did this, it's all good. And the fifth would be to now include the latch. So we substitute the latch stepped model for the manipulated input, which means that we already know that A of S is a step at time 0. So it's actually Fa at the time of 0, that's 1 over S. I don't know if you've seen this, but 1 from continues to from time to Laplacian is 1 over S. So we can substitute this in for our Fa. Which means in the sixth step, we can now find the continuous time step response. And so we first need this to be solved for V of S, right? And I'll put this here. So now V of S is actually 1 over m times S plus V times m times V of t equals 0 plus Fa time equals 0 over S. Is this clear? We put basically this over there, and that's why it's 1 over ms plus b. And over here we had m times v of t of 0. And if this is not the latch, right? So at point 6, we now try to find the continuous time step response. Basically, the back transformation. We try to get this back into the time domain. What we usually do is use tables, because this can be very, very tedious, but a lot of mathematicians already did the work for us. So there's all these different Laplace tables. And let's see here. Might have not brought it today. Okay, I forgot to bring the table with us, but I'll give you what the table has. So I will use this here. So I had a table that tells 1 over S equals A becomes e to the minus at. And I also use A over S times S plus A is 1 minus e to the minus at. Okay? Because this is something, S times S plus something, and this is just this over that. Okay? So we have to get it to that format first. Shouldn't be so hard. So first of all, we do this for B times 0. We try to get into this format. So it will be 1 over S plus B over M. And to get there, we have to put out the M. And that cancels with that M, right? So that should already be the correct formula.
That's the first one.
And then for FAT is 0, we have to get it to the format of
1 over M.
B over M